In Macomb County, the average household spends $186 a month on electricity. Now that doesn't sound like a lot, but over the course of an entire year, this number adds up to $2,232. Over, say, 20 years, that number becomes $40,640. That's a lot of money. Solar panels, a form of renewable energy, could be a potential way to reduce this amount for people all across Metro Detroit. But there is one small issue. Michigan is not really well known for solar panels. We're ranked 27th in the nation on our solar panel data, and only 1.67% of the state's energy comes from solar power. This is mainly because Michigan is a cloudy state. We're one of the cloudiest states in the country. And what this means is many people overlook solar power for other forms of renewable energy, like wind, for example. However, with solar tracking, a technology where a solar panel will follow the sun throughout the entire day, this could be maximized to get as much energy from these panels as possible in places like Michigan. This would increase the amount of renewable energy that households are getting, while also reducing the costs for people in their everyday lives. My name is Morell, and this is the effect of solar tracking on power produced from solar panels in Metro Detroit. In this presentation, I'll be going over my background information, my problem and hypothesis, my procedure, the results I got, my takeaways from these results, and my improvements and future research to consider. So first, let's start off with some background information. Everyone knows the basics of how a solar panel works. The sun's energy hits a panel, and then magically energy is created for us to use. But how does this really work? It works through something called the photoelectric effect. You see, a solar panel is not just one giant machine. It's actually composed of smaller solar cells, also called photovoltaic cells, that actually produce this power. How it works is the sun is composed of photons. As these photons hit each singular solar cell, there's a semiconductor in these cells that makes electrons free themselves from their position on the panel and travel through the grid-like structure on a solar panel. So if you've ever wondered why a solar panel has those kind of grid-like shapes, that's actually what the electrons travel through and how energy is produced. This power goes into a solar inverter, which then converts the energy from DC direct current to AC alternate current. What this means basically is how the energy travels. Direct current is where energy travels in a direct direction, it's in the name, but this is a less efficient form of energy over long distances compared to alternate current, which is where the energy can invert directions and is more commonly used in our households and the electric grid, which is why the inverter has to convert it. Another key term to understand is flux, which is simply how many electric field lines pass through an object. In this experiment in particular, I'm talking about photon flux, which is how many photons are going to hit a solar panel. So what this means is as more photons hit a solar panel, more energy is going to produce. Less energy is going to be produced when there's less photons. It's why a bigger solar panel just logically produces more energy than a smaller solar panel. Another key term to understand is what kind of solar tracking I'm doing. I'm doing a single axis form of solar tracking, which means the panel will be rotating on only one axis, and it will be rotating vertically across a vertical axis instead of horizontally. So now my problem and hypothesis. My problem statement was to determine how much more efficient a single axis solar tracking system was at producing solar energy in kilowatt hours than a fixed panel in Sterling Heights, Michigan. I hypothesized that the solar tracker would produce 15% more energy than the fixed panel. But first, I had to actually build a tracker. This process is what took up most of my time. I had to use a lot of materials to do this. I used 2 light-dependent resistors, 2 aluminum angle brackets, a 100-watt solar panel, a 12-volt battery, an Arduino Uno, copper wire, a control box for the Arduino, control relays, and a 90-volt permanent magnet DC motor. Additionally, I also had to use a solar controller, a solar inverter, a watt meter, wire lugs, an industrial light tripod, a V-belt, a steel angle bracket, a 7-inch pulley, and an LCD display system for the Arduino. Now, all these materials weren't used for the exact same thing to build. The first thing I had to do firstly is build the solar panel mount, which was done by screwing in the aluminum angle brackets into the panel, which eventually looked like this. Another hole would then be screwed through the two to be placed onto the actual light tripod. To do that, I had to 3D design some parts. Firstly, this part was a clamp to actually put the motor onto the industrial light tripod. I had to use 4 of these because of the weight of the motor. It would just not be supported by one. And then another part that had to be built was a bearing placed on top of the industrial light tripod to actually rotate using the pulley and mechanism of the solar panel. This is what that top of the industrial light tripod looked like. This is the bearing I just talked about, which is where the rotation happened, using this 7-inch pulley connected to the actual motor. The steel angle bracket on top is what connects those aluminum angle brackets I just talked about with the panel on them to the actual design. Additionally, the control box of the Arduino had to be found in a 3D printed just to protect the Arduino from the natural elements, as this was going to be outside. I had to code the Arduino to actually get this to work, and I'll talk about the process how this occurred. Firstly, the Arduino had to be connected to a laptop to actually code it in, and this was connected with the LDRs and control relays to actually make it work. But how it worked, basically in the code, was that when the sun would shine on the light-dependent resistors, these resistors would get a value, and that value would basically be how much sunlight each side of the panel was getting. They would send this value to the Arduino, which would then translate it into a value it could understand. Kind of like translating a language, like French to English. It decided, should the panel move left, right, or should it stay in place? After this, the Arduino would send that decision over to the DC motor to then actually rotate the panel. Here's a procedure video of what that actually looked like. As you can see, their light-dependent resistors are on the panel, and then there's a solar controller on the actual design showing the voltage that we're getting from the battery. This is what the panel looked like as a whole, with light-dependent resistors on each side. And then inside the garage was actually where the watt meter was, which would give me the data from each day, displaying in kilowatt hours. I'm sure you want to see the panel actually moving, so here's the front-facing version of it. The panel moves quite slightly and then in a large amount. This would sometimes vary, which we weren't exactly sure why. But then this is also a video from the back of showing the panel. Now this is a much slighter movement, so it's kind of hard to tell. But if you look at the pulley and the V-belt, you can kind of see it move. And I can show that again. It's very slight, but that's kind of the amount of movement we wanted over the course of an entire day. Now, after we got this solar tracking working, what results did I get? So firstly, my plan was to do a 2-sample t-test looking at the power produced from both the fixed panel and solar tracker, and then use a % difference to see how much more effective the solar tracker was than the fixed panel. But I couldn't do this at the end of the day. It's because to do a 2-sample t-test, I needed a random sample, which I did not get, ultimately, just because of time constraints and things like that. And if I didn't have a random sample, I also needed to have no outliers or skewness. In addition to that, you also need to have sample sizes greater than 30. And if that's not the case, if you have less numbers than that, you need no skewness or outliers, which once again I didn't have. Which meant I had to do something else. Which meant I used descriptive statistics for my observations to determine the results of my experiment. So here's a box plot of the power produced from both the solar tracker and fixed panel. The fixed panel, as you can see, has a mean of 0.09, and the solar tracker has a mean of 0.05. Now, there's quite some skewness in the fixed panel, with the median being 0.055, indicating that there were some values that pushed this data over. It's important to note that these box plots aren't the best form of descriptive statistics to use just because of my limited number of trials. So I'll also show the dot plot for that. And as you can see, there is a group of data trials that seem to be much larger than the others. This is also sort of the case for the the solar tracker, but just definitely not as much. So when I looked at this, I tried to come to some conclusions, and so I decided to also look at the temperature to see if maybe there was something going on there to explain why so much more power was produced from the fixed panel. And looking at this, there is quite a difference. If you look at the minimum and maximum temperatures of the fixed and solar trackers and see the difference, it's quite extreme. There's no overlap between either of them, which could be a big area to look at when determining my scientific results. The dot plot just also conveys this information. I also wanted to look at the voltage of the battery to see maybe if this battery, creating a smaller amount in solar tracking trials, for instance, could have reduced the amount of energy it collected. But there was much more overlap in this case, leading me to believe that this was not the biggest cause of why I got the results that I got. Finally, to also look at my results, I did the percent difference equation, but instead I used the fixed panel because it had the greater mean. This equation was the fixed panel minus the solar tracker over the solar tracker times 100. Reminder that the mean of the fixed panel was 0.09 and the mean of the solar tracker was 0.5. When I did this equation, I got an 80% difference, indicating that the fixed panel was 80% more effective than the solar tracker. And this is quite significant because a solar tracker, even if it's not working properly, should produce the same amount of results as a fixed panel. So what happened to have the fixed panel have greater results? My hypothesis was clearly rejected. I had believed that the solar tracker would be 15% more effective, but the fixed panel was actually 80% more effective. So really, what happened here? The biggest indicator I saw for this reasoning is that I did my trials for both at different time periods. My fixed panel trials were done in late October and early November, while the solar tracking trials were done in late November and early December. Firstly, the earlier fixed panel trials would have had more sun naturally because of temperature, but there's also another phenomenon with the temperature that could have caused this occurrence. You see, the flux I talked about earlier comes into play here. Earlier in the year, the sun's path is going to be higher up in the air and give the panel more area over the day to produce energy, compared to later in the year when it will be at a lower angle and just not hit as much of the solar panel. As I talked about earlier, flux is the key thing here. If you have less area, you're going to have less flux, which is going to mean less energy. So now that I have the results and my reasoning for the results, where could I improve this experiment to truly find the results that I wanted? Well, first off, I have to talk about other errors in the experiment. There were 2 occurrences where the panel fell over during trials, and this panel was pretty sturdy, but over the nighttime, Michigan had some 40-mile-per-hour winds at certain days, which the panel just couldn't handle and fell over. It's important to note that the second occurrence of the solar panel falling happened right before I was about to finish my solar tracking trials, and it seemed like the panel wasn't working correctly like it used to, which made me end my trials early. Additional errors was that I couldn't do a random sample and the time constraints of doing my limited number of samples, which meant my data was more inconsistent and not as objective. Additionally, the battery, 12-volt battery, had to be replaced midway through my experiment, simply because it was an older battery and didn't seem to be holding charge anymore at the end of my fixed panel results, which made us replace it for a newer battery for the solar tracking trials. But as noted on the results, it did not seem to be different than what had earlier occurred for the fixed panel trials. So what would I do to improve this? First off, to stop the solar panel from falling, I would build a better design overall for the panel. This mount design is a good idea to make it rotate, and it would also be an easier design to replicate for other people that are wishing to also do solar tracking and apply it to their solar panels at home. A way to fix most of my problems would have been to do 2 solar panels at the same time, 1 fixed panel and 1 solar tracking panel. The issue with this is just costs. A 100-watt solar panel is quite costly, which meant if I did this again, I'd probably scale my experiment down just to be able to do 2 at the same time and reduce my errors. Another idea to talk about is doing dual axis tracking, where the solar panel rotates in both the horizontal and vertical direction at the same time. This is a much more advanced form of engineering, which couldn't be done now, but it could be an interesting way to explore how much more effective dual axis is from single axis and then from the fixed panel. In my acknowledgements, I'd like to acknowledge Michael Craig, an assistant professor in energy systems at the University of Michigan, for replying to my questions and helping me figure out why I got the results I did. Mr. McMillan and Ms. Cebulski for understanding the highs and lows of senior research and being very considerate and helping me out. And I'd also like to thank my dad for helping me in my procedure. He helped me if there was any blocks in my coding or my design and helped me build the panel overall. I couldn't have finished the procedure without him. Here are my references. Thank you for watching. Are there any questions? Okay.
So how did you come up with 15%? Why did you think it was going to be 15% improvement?
Similar research had been done, but the research on solar tracking had been done in areas much closer to the equator, like Malaysia and Saudi Arabia, and they produced results 30% more effective, but Michigan is just at a higher latitude level, so I wanted to reduce this number, but I still determined that the solar tracker would be more effective.
Okay.
You guys are allowed to ask questions, you know that, right? You're supposed to help them out, make each other look good.
What's your question?
How much do the solar panels cost?
Solar panel, it costs depending on the wattage of it. So this was quite a large panel. I'd say regularly this panel costs about $300, but I had it, my house has some solar panels, so I was able to have an extra one, so I didn't need to spend that money. But doing 2, it would have cost a lot of money. Damien?
When the solar panels got knocked over, did you think of how to make it more stable?
Yeah. So I honestly didn't think the solar panels would be knocked over just because the motor was so heavy and the light tripod was quite stable, but I guess those wind gusts were just too much. So yeah, I thought a mount system was actually kind of closer to the ground and it was more connected, as I showed in that one slide, I thought could be a better design to build and try out if I did this again. Rizal?
What inspired you to do this?
I wanted to do research that seemed to be at least a little that I could apply to the world around us and Metro Detroit in particular. So I thought solar energy, it didn't seem to be quite a popular thing in Michigan, so I wanted to see if we could make it better. Mr. Miller?
You talked about the photo sensors on each corner of the solar panel, and they kind of told it which way to go.
Yeah.
Did it turn towards the one with more voltage or the one with less voltage? How did it kind of know which way to turn based on those sensors?
Basically the sensors each value would independently go to the Arduino, and then the Arduino would basically see in the code if the LDR1, because it was labeled LDR1 and LDR2, if LDR1 was greater than LDR2, then it would rotate in that direction.
Okay, so went towards the greater voltage.
Yeah.
Okay.
So now that you built this, is this something that was still going to stay hooked up that would save money?
Yeah, I still have the solar panel up. When it's sunny days and it feels like it's worth it to turn the panel on, I'll still turn it on and make it work. But it doesn't seem like the solar tracking is if it works as well because of the fall damage and things like
So
that.
it's working just like a regular solar panel then?
Basically. Lily?
Do you know, with the energy or whatever you collected, what you could do with it?
Yeah. So the panel was connected to the watt meter, so all the energy that I was getting was kind of going through there. and this energy was just going back into the electric grid. So it was decreasing our energy bill a little bit.
But you didn't figure out how much?
Well, it was on the watt meter. That's how much energy
So,
was.
do you
going
have
back.
an idea of like how much? Like
Yeah,
$10 a
it
month?
was like the means. And energy costs, it's really not that much. I didn't look that one up.
Okay.
But it wasn't, just one panel's not gonna completely reduce your bill.
You had to 3D print some parts, where did you do that?
In Tinkercad.
And what printer did you use? Did you use one here, did you use one at a shop somewhere?
My dad has a small printer for like his business and stuff at home, so we use that. But yeah.
How many panels do you think you'll need to like actually see a difference in your energy bill?
It really depends on your house and how much energy you use. I'd say around, it does depend. I think we have 4. How much energy do you think the 4 panels saves?
I think around $40 a month.
Summer, it's usually a lot in the summer, it's a lot more, it's like maybe 20%.
Yeah, so like that's a pretty significant reduction. So like you can really for the cost, it's really an investment because you're just going to continue to see decreases in your energy bill. But yeah, 4 panels I'd say would be quite significant.
Alright, good job.
Thank you.